Okay. So we're on this example problem. So we look at the formation constants on table 12.2 for a calcium Y2 minus. We would get the K of that. Well, it's not a PK because it doesn't have a negative sign, but it's log of AK. So you take 10 to the power of instead of 10 to the negative power of. Yeah. Huh? Oh, shit, yeah. Okay. Thank you for reminding me. Yeah, I came in and everybody was doing tests, so I've had to boot a lot of stuff up that normally would be booted up. Okay. That should be going up there. Okay, so we're doing an example problem. We're doing the KFs for this. Remember, KFs are the log of, not the negative log of, right? And so when you use them and look them up, the KFs are going to be 10 to the power of those log of KFs that you get in the table, okay? Again, remember that they don't do the full KFs because that would require more printing, right? And more space. So you're going to calculate your concentration of calcium 2+ in a solution of 0.1 molarity calcium Y2 minus at pH 10 and at pH 6. First off, what sort of behavior would you expect from going down in pH? So this calcium right here is a 2+, right? That means this Y is 4-. When you go down in pH, when you go from pH 10 to 6, you have less of the form of Y4-, right? And so what does that mean? Well, you should see more concentration of calcium ion going into solution, right? Because you have less of the Y4- to bind to it. Okay, so we'll use these values. Your complex formation reaction would be the calcium 2+ plus the EDTA. This would yield the calcium Y2-. Your KF is going to be a modified KF because we're going to be doing this for different pH levels, and even pH 10 is not 100% the Y4-, right? So you have to do the activity of the Y4- times the KF, okay? And again, this is actually a derivative of those activity formulas that you looked at before, right? So the term in here would be a Y4- concentration. And typically you can move those activities out in front. And the only activity that's going to change is the Y4- one, right? So the rest of them will go to unity. Or 1, right? Okay, so again, EDTA is going to be on the left side of the equation, will be the EDTA in all of its forms. So that will be EDTA in all of its forms. If we use the activity of Y4 or gamma 4-, are you guys okay if I say Y4-? It's just easier to say. Okay. You know what I'm talking about, gamma, right? Okay. Okay. Yeah, it's just easier for me to say, as you can probably imagine. So at pH 10, we get an activity of 0.3 off of that table. Remember the activity table? The lower pHs give you larger activities, or activities closer to 1, right? That's why typically you use a buffer solution up in the pH 10 to 11 region. And then this would be your KF right here. You multiply those together, that will give you your modified KF, or your KF at that pH, okay? And you all are aware that this prime, that's what that means, right? So prime always means at modified conditions. Okay, yeah, it showed up a lot in biochemistry. Probably remember that there. Shows up a little bit in other classes, but most of the professors don't bother telling you. That's what that means. So again, another one. Technically speaking, this would be better served to either have a dual prime here, double prime, or to actually just label this as KF10, KF6. That would be what I would do. So I can't, screw up and mix them up, okay? Yeah. You can keep the prime if you want, because it's still a modified one, but I usually put an extra label down here, next to the F, because then you don't mix them up. Anyways, the KF6 at pH 6, the activity is much, much lower at 1.8 times 10 to the negative 5, right? You multiply those again, you get a value of 8 times 10 to the negative 5th. And notice that's a factor of what, 100,000 difference? Pretty big difference. Okay. So now that we have K values for those pHs, what can we do? Well, we do an ice problem essentially, right? So we're going to look at this as if we have no calcium, because the only place our calcium can come from is the complex. We have no EDTA other than stuff in the complex. Because notice that's the only place we get it from. See that? 0.1 of that complex. And so we start with 0.1 molarity of the complex. What will we have for the final concentration? Well, that's going to be whatever we split up into from the complex, so X. And EDTA has to be the same amount. Now, when they split up, the EDTA will differentiate. It won't all be the Y4 minus, right? Some will be the Y3 minus. Some will be the 2 minus. You get the idea? It'll get protonated. We don't care. That's not a concern of ours, okay? So, we'll have 0.1 minus X for the final concentration of our complex, because, some of it has to split off. We get our equilibrium expression. You will notice here the equilibrium expression has this complex on the top, because we're starting with the product of this, right? Be careful that you understand what a KF is. That tells you which direction this equilibrium is going. So KF is formation, right? Notice that this equation right here is formation, right? Dissociation would be the opposite way around, right? So many people get confused about that. Don't forget, you're doing formations, not dissociation. That means your equilibrium is this direction, forming the complex, right? As your product. If you mess up, you can actually do this. You just have to take 1 over, don't you? That would work. You just have to flip everything. Okay, so we plug these in. Again, we have a 0.1 minus X over X squared. Notice it's that same relationship again, because they're 1-to-1 ratio, right? And so we plug in our K primes. So we do the pH 10 version is up here. The pH 6 version is down here. We would then do our math. You could just do a quadratic and you get the right answer every time. If you have formulas set up to do quadratics automatically for you in your calculator or on an Excel spreadsheet, just do quadratics. It's fast, it's easy then. If you have the formula so you have to do it by hand every time, you might want to assume this minus X, you don't have to put it in and see what you get. Because it could save you a lot of time, right? When I went through this, by the way, I had formulas in my calculators that I programmed in and did this. But I allow you guys to use spreadsheets so you could do Excel. It would be faster to program it. So. Okay, you get an answer of 2.7 times 10 to the negative 6 and 3.5 times 10 to the negative 4th at pH 10 and pH 6 respectively, the larger number at pH 6. Because at pH 6 you have less of the Y form minus form to bind it. Okay. Notice both these numbers are far lower than 0.1, so you could have assumed this minus X is meaningless and simplified your math here. Okay? All right, does anybody have any questions? Notice again, your math is greatly simplified. Much less work has to be done here because all we're looking for is the calcium species, free, the calcium species. We don't care what the EDTA is and what form it is in, do we? So we can assume whatever dissociated EDTA is in, we don't care. It is just free EDTA, right? If you could not assume that, then you would have to do those multi-ice problems. Remember when you feed one into the other? From high concentration to low concentration? That we talked about before? The multi-equilibrium? But most problems here you don't have to. You don't care what form EDTA is in. You just care what activity it has at a pH. Okay, so this is going to be EDTA titration curves. Again, we can calculate the concentrations of free metal during its titration with EDTA. So if the K prime F is large, we can consider the reaction to be complete at each point in the titration. Your titration curve is going to be a plot of PM versus the volume of EDTA added. You'll have three natural regions. So here we see PM, that's the negative log, you know, like pH, but for metals, right? Is everybody okay with that? So M to the N power is a metal of whatever charge, right? Calcium 2 plus, whatever. This is a P, just like a pH, right? It's a negative log of. And that just gives you a more linear relationship. Remember, this would be a logarithmic relationship otherwise, right? So it would look real ugly. So it's basically a pH for metals. And this is the volume of your titrant, right? So your volume of your standard you're adding versus the pH, but for metals, PM. Okay, so again, you're going to have three regions just like you would in any other titration with an acid base. Region 1 will have excess metal. You're going to be taking off and removing the excess metal. Region 2 is going to have your equivalence point. It'll be halfway through your large, your high slope region, right? Your region of maximum slope will be your region 2. That region 3 will then, of course, be the excess EDTA. So you'll be putting in EDTA, and you have excess EDTA. Notice that this region, you never actually get to zero metal, right? That's not possible. Because some metal is always going to be free. It'll approach zero metal, but never get there. Okay? Anybody have any questions? Fantastic. It looks very similar, right? Very, very similar. So region 1, before your equivalence point, of course, your concentration of free metal is going to equal to the concentration of excess unreacted Mn2+. So whatever metal has not been reacted, that's your excess that remains, right? Region 2 is going to be your equivalence point. Equivalence points always are where the two things are equal, right? So your metal, it will equal your EDTA. Region 3 is going to be after your equivalence point. The concentration of excess EDTA that's added after equivalence point, these are going to be based on your saturation of your KF, essentially. So remember that it will not bind all of the metal, but that will go to zero, right? And your amount of EDTA that's free will greatly exceed the amount that's bound, that is free metal ion, once you're in region 3. You're looking at how well it binds. So let's consider this reaction of 50 milliliters of 0.04 molarity calcium. This is buffered at pH 10, which is the normal buffering for EDTA, if you're curious. This will have 0.08 molarity of EDTA. And so again, Remember that you always have to look at your activities for these, okay? So you're going to always use a K prime F for your equations, for figuring out how much metal ions free, for all these things, okay? So you always end up looking at that table. What is that, 12.2 or something like that? You know the table I'm talking about though, right? That has the pHs from 0 to 10, or 0 to 14, and then activities of the EDTA next to it. You always need that table, and you always need the KF table that is the log of, not negative, just log of, KF. Okay? So every time you do these problems, just remember, get those two values, okay? So you plug in your activity for your Y4 minus, which is the binding form of EDTA, times your KF for that metal, which is calcium in this case. So it's 10 to the 10.65. Again, we get that same value we actually already did in the previous example problem. This is calcium again. So in this case right here, you would want to figure out what region you're in. So we have the reaction of 50 milliliters of 0.04 versus this 0.08. So after the addition of 5 milliliters of EDTA, we would be in the first region, right? Because that's double the concentration, so it would take at least 25 milliliters of the EDTA to be equivalent, right? Okay. So what we do is we're going to figure out how far away we are from the equivalence point, right? And so it would take 25 milliliters to reach the equivalence point, minus 5 because we went 5 milliliters of that to it. This would be divided by 25. This would be your fraction of calcium that remains. The fraction of calcium that is not binded to EDTA, right? This would be your original concentration of calcium. So again, you're doing the fraction that remains free times your original free concentration, right? Which will give you your current free concentration. And then we have to correct the volume. So remember, you're adding volume, right? So whatever concentration you had is just diluted in the first place. And so it's the V1 over V2 here. Initial volume divided by the new volume. And that's your volume correction. Anybody have any questions about that? Is that pretty straightforward? If you do have questions, please do ask questions. Or come into my office hours if you don't ask them here. Something. Get those points clarified. So what are we doing at region 2? Well, at region 2, virtually all the metal is going to be in the form of the calcium Y2 minus. Because remember that this will be equal amounts of the EDTA and the calcium, right? And these KFs are typically pretty damn large. So that means they're going to bind the vast majority of the calcium, right? So virtually all the metal gets bound. This is going to be essentially equal to the original calcium 2+ with a correction for dilution. So the calcium bound to the EDTA Y4 minus form is going to be the original concentration of calcium corrected for its dilution factor. And its dilution factor, of course, is going to be the new volume, right? In this case, region 2, we had to have added 25 milliliters, didn't we? Where did I get the 25 milliliters, by the way? Right here. This and this is double this, isn't it? So I half that volume, and that would give me equal concentrations. See that? You can do that with your calculator if it's not something simple, but you know, all my examples are something I can do off the top of my head. At least I try to. Okay. And so this is that dilution factor again, V1 over V2, right? And we get our new concentration. Remember, this will be for the bound form. Once you have the bound form, you can then do a simple ice problem where you start off with 0 of each, and you see how much of the bound form would come apart due to the KF, right? And so essentially all of it's going to be in the bound forms. We put that as what's the bound form. The final amount would be whatever is, coming apart from the bound form, right? And so we then use our modified KF. We plug in these numbers. Typically, these problems, you'll be able to assume that minus x, you don't have to actually, you can just assume that doesn't matter. Because these KFs are very large numbers, right? Typically like 10 to the 10th, 10 to the 5ths, 10 to the 20ths, okay? Okay, so you do your math, you get x equals this. That is the concentration of your calcium that is free. You can then get a P calcium, negative log of calcium, by taking negative log of that value, of course. And that would give you 5.85. Anybody have any questions? No? Yeah, it's pretty much exactly like you'd expect from like an acid-base titration, that sort of stuff, right? And the only real difference here is that these reactions don't go to completion at the equivalence point, okay? The equivalence point is where the two concentrations would be equal due to the fact that this has a KF, this has a binding constant, this is a formation constant, this is not going to go to completion. It will always have a little bit of free species in the solution, okay? Okay, so region 3 is after the equivalence point. Again, virtually all of the metals can be in that same calcium Y2 minus form. It'll just be slightly more every time. You're going to have diminishing returns in these cases. So you do pretty much the same thing. It's the same problem as before, okay? So you're just going to figure out your EDTA amount. So you figure out your EDTA after the equivalence point. So we're at 26 milliliters. That means we have 1 milliliter of excess EDTA, right? So here's your EDTA excess. It's going to be the original concentration of EDTA times the amount that it's over the equivalence point divided by the total volume. And that's your new concentration of excess EDTA. And then you have the equivalence point amounts for the bound complex, right? So again, all of the calcium is in the bound form is what you're assuming at this step, okay? So you do all of the calcium is in the bound form, you take the original calcium concentration, it'll be the equivalence point volume, 50, divided by the total volume for the dilution factor, and that gives you your concentration in the bound form. You plug that in to your formation constant expression, just like you've probably gotten used to at this point. And so your formation constant expression will have the bound form that we just calculated right here, that calcium Y2 minus form on the top. It will have the free calcium, which we don't know, which we're trying to find. And it will have the free EDTA as your EDTA amount that's dissociated. Why is that? Well, this is going to be vastly more than the amount of calcium that would be free, right? So the amount that disassociates is going to be nothing compared to the excess EDTA we put in, right? So we can directly plug that into our EDTA amount. Yes, technically it would be EDTA plus X, right? It'd be this value plus X. But your X value is going to be so small, it doesn't matter. Okay? And just like this would be that concentration minus X, right? But again, X is going to be so small it won't matter in these cases. Okay? Everybody's okay with where we're at? No questions? You work it. These are very easy because you don't have any, only one extra, right? So literally you just gotta do this math right here, this divide by that, and then cross multiply, and you're done. You get calcium concentration, it's very small, it's far smaller than these, so you don't have to worry about that X being too big, and your assumption being wrong. You then take the negative log of it, and you get the PM, or P calcium in this case. Any questions? No? Okay. Notice that these graphs, just like the acid-base ones, this equivalence point depends on your KF. So if you have a smaller KF, this equivalence point will go down. Okay? And this equivalence point going down means that this comes off at a lower level. See that? So this starts going into that diminishing returns at lower levels. Okay? Yes, they all will eventually head up to, 0, but it will take a very, very long time that you don't want to bother looking. Yeah, I put in 10 tons of the stuff. I'm still not at 0. Damn. Okay. Do you have any questions about this? No? All right. You can, of course, do this with spreadsheets. It really is a huge time saver, obviously, when you do this with spreadsheets. I'll be very honest with you. When I did this in labs, I did it in spreadsheet, and then I never did the math again. I just had different spreadsheet parts that give me different, unknowns. So, yeah, pretty much what should happen. And then you'll forget all the formulas, and you'll be like teaching it or something later. I don't remember any of this shit.
Are we always going to be working with the
Pretty much. That would be a more advanced chapter where mu is not equal to 0.1, so you can't use that table. But again, you can do the same activity stuff as you were taught in the previous chapters. You can find those activities yourself. There's no reason you have to use that table. Like in fact, if you do the spreadsheet correctly, that actually is the easier way to do it. Yeah, you take a spreadsheet, you set up all your equations, and then you plug in the values that would derive mu automatically, and then would calculate gamma automatically, and so you never have to look anything up. You can just plug in all the concentrations that you have in the problem. Like if you do the spreadsheet right, that's the easy way. Because, you doing extra math steps doesn't matter if you're using the spreadsheet. Right? Yeah, it's kind of funny, right? That a lot of times in analytical chemistry, that's true. The tables are meant to save you time, but they only save you time if you're doing it by hand. If you have a computer doing all your equations for you, they're actually longer to use the tables, right? You're better off just doing the math. Yeah. So whenever you calculate activity, you have to calculate mu first. And all of those things all use the terms for the concentration that would be in your original problem, right? So if you set it up correctly, I used to have a spreadsheet. It's probably gone by now because I've changed accounts a few times now. But when I originally took this, I actually had a spreadsheet that a computer program on my calculator actually, because I couldn't use spreadsheets. But I had one that we would enter the concentrations for your different species up to 10, and then you'd enter the charges, and it would actually figure out the, and then the amount, the equivalent, the stoichiometric amount. And it would automatically then calculate everything else. You know, most of the stoichiometric amounts are 1 anyways, so I usually didn't change that. And the charges, I just change the charge if I need. Most of them are pretty similar. And so it would take me, you know, like 10 seconds to enter it. And I'd always have the answer for exactly that problem. No matter what the concentrations I'm used were. You wouldn't even need, like nowadays with spreadsheets, you wouldn't even have a limit on the number of things. You could do more than 10. I just couldn't do it because it's a calculator. I had to program it. All right. So here's the mass balances for the metal and ligand. So there's two forms for the metal. There's the free form, and then there's the bound form, right? So we'll go ahead. Oh, I didn't even talk about that. So we have a titration of a metal ion, right? The metal ion will always be the initial concentration of your metal, Cm. The volume would be Vm. The solution of your ligand, the concentration will be Cl, of course. The volume would be Vl. When you're talking about EDTA, remember it's a chelating agent, so it's going to completely bind your metal, right? It can bind anything with a charge up to 4. Notice there's not a lot of stuff with charges greater than 4, is it? Okay. So the mass balance for the metal and the ligand would be this right here. Of course, the metal is going to be the two different forms of the metal. The free metal, ion, and the complexed metal, right? Those would just be added together, and that would be your total concentration of metal. The other way of expressing that total concentration of metal is the initial concentration of the metal times the volume, C1V1, right? Divided by V2. You see that? That's all you're doing here. So your total volume, VM, VL, is on the bottom. Okay, so that's your mass balance for the metal. Your mass balance for the ligand is just going to be, well, the same damn thing, right? It's just that all the M's turn into L's. And all the L's turn into M's. So concentration of free ligand times the bound ligand will be the initial concentration of ligand times the initial volume of the ligand divided by your new total volume, right? Notice that your mass balances automatically whenever you look at these equations. If you're doing a complex situation, a complex solution, you already have two equations, don't you? Of those equations you need to generate. You have those two mass balances. So if you substitute the Kf times the metal concentration times the ligand concentration from your equation 12.8 for the mass time the bound complex, your bound complex concentration in your mass balance. And this is just what complexes look like, by the way, right here. If you're ever curious, it's the top view, that's the rounded view. This is your potential in terms of pH. Notice you get a fast drop off up here at at the higher pHs, pH 9, pH 8. So then you'd substitute your expression for L from the equation 12.10 back into the equation 12.9. You'd solve for the titration, fraction of titration. That's the fraction of titration symbol, by the way, in case you're ever curious. You do not actually see that very often. I actually can't think of any other example where it actually is demonstrated what symbol that would be. So I think this is the only place you ever see it. So, just in case, this is where you find it. Okay. So this right here is the results of those steps we just went through. That's the result. So notice we have the ligand portion right here over the metal. Concentration of ligand times volume of ligand over concentration of metal times volume of metal. Those are the sum of those left terms, or I guess it was on the right for you guys. And then this would be the substitutions that we made. If you do this calculations, either one of those, it would be the fraction of titration. How far are you along titration? You can do the same thing using a spreadsheet. This being phi right here. Anybody have any questions? This is just the same thing with the spreadsheet. And you can do it incrementally on a spreadsheet.
Are those each like just different equations put in for like PM and
Yeah, so this would be D4 right here. So we go to D4. It would be the 1 plus. There's the KF. Okay. And then E4 right here, that's the volume of ligand. Right there. And that's just that calculation for a volume of ligand that we saw. Okay, so for how many metals to be titrated in alkaline solutions with EDTA, we would use an auxiliary complexing agent. This will prevent the metal hydroxide precipitation. So remember that many metals are insoluble with the hydroxide, right? So in basic conditions, you're generating hydroxide if it's in water, right? And so there is a problem with many of these titrations with EDTA that you may not have thought about before. And that's that you have high hydroxide concentration, metals typically are insoluble with hydroxide. That means a lot of your metals would be precipitating during these titrations, wouldn't they? That sounds like a problem, doesn't it? And so what you use is an auxiliary complexing agent. It's something that would complex well enough that it would prevent the hydroxide from binding, but it doesn't complex so well that it would prevent the EDTA from binding. Think of them as like EDTA is a very strong chelating agent. Think of these as less strong than EDTA, but stronger than OH. Okay? Okay, so the reagents are ligands, such as ammonia, tartrate, citrate, or triethanol amine. You'll notice that we'll end up using one of these complexing agents when we do this. If I remember correctly, it's off the top of my head, it'd be titrate, I believe, or citrate, excuse me, that we use. But it might be triethanol amine, that's a pretty common one too. Both of them would be very effective. They must bind strongly enough again to the metal hydroxide to prevent precipitating, but weakly enough that they can give the metal up to EDTA. So they have to be a moderate one, right? This is citric acid, by the way, and yes, it is, citrate, citric acid, as in like fruit. Okay. Anybody have any questions about that? Good. Guess. Okay, let's consider a metal ion that forms two complexes with your auxiliating complexing agent or ligand. You have the metal forming a complex with your ligand. That would be beta 1. Your second complex would be beta 2, just like all the other complexes that we talked about, right? Beta 1, beta 2. In this case, we just have beta 1, beta 2. Beta are the cumulative formation constants. So the fraction of the metal ion in the uncomplex state would be your M. So this would be concentration of M over the total concentration of all metal species would be your fraction of metal ion in the free species, right? Which would be denoted by alpha M. Yes, I hate that too. I wish they had made the fraction and the activity different symbols and not had similar things, right? But you can figure it out by the context. It's okay. You'll manage. So M total is again the metal in all of its forms. It's the ones bound to the ligands. It's the free metal. It's all metals in all forms. So your mass balance of M total equals metal in all its forms, right? The metal ligand, the metal ligand 2. If we take equations 1213 and 1214, this would allow us to do these equations as well, which is simply substituting these things in, right? So the metal times the metal ligand form would be the beta times the metal and ligand concentrations, and so on. Notice that those are just equilibrium expressions, okay? If we substitute these in, we see that we can get this form right here. Notice this form's all in metal and ligand terms. There's none of the complexes in this form of the equation. So we can simplify. And we're left with just constants, ligand, and metal terms. How wonderful, right? Okay, we substitute that into our fraction equation. What we see is the metal terms actually cancel. And so the fraction of the metal is in ligand terms. And everything else is constants. Isn't that beautiful? Don't you love it when you have a fraction of something and it has no terms for that substance? So the metal ends up being all the fraction of metal in the free form is entirely dependent on your ligands, right? Which actually makes sense if you think about it. But I do find that funny. Zn2 plus and ammonia form complexes, which are these complexes here. Notice there is 4 of those because ammonia is neutral. So combined to the different spots. If the concentration of free unprotonated ammonia is 0.1 molarity, let's find the fraction of zinc in the form of zinc 2 plus. At any pH, there's going to be some of the ammonium in equilibrium with the ammonia. So the appendix 1 is going to give you formation constants for your complexes. Here we see the different complexes labeled B1, B2, B3, and B4, right? For the 1 ammonia, 2 ammonia, 3 ammonia, 4 ammonia, you get the idea, right? Okay. So if we put that then to our equation that we just derived, again, this is going to be for the 1, 2, 3, and you would keep going. You can see the pattern there, hopefully. Okay. We plug that in, and that's going to give us our fraction. So we go 1 over 1 plus B1, which is right there, times the concentration of L. The concentration of L is this one right here, plus B2, concentration of L squared, B3, or beta 3, excuse me, concentration of L cubed. You get the idea. Plug those in, do the math. We'll get that the fraction of free Zn2 plus is 1.8 times 10 to the negative 5. And so what we see is there is very, very little zinc 2 plus in the presence of 0.1 molarity ammonia. Anybody have any issues with how I did that? Anything you don't understand? So these come in formation constants, come in that log of. So we have to take 10 to the power of 2 point, etc. This case, you have 4 of those, so you'd get 4 of them from the table. That's that. The 0.1, because this is going to be a small number, you can just plug in 0.1 for your ligand concentrations in each place, right? None of it, not enough of it gets used up that you care. That's going to matter. And that's typically true of all ligands because formation, you're using something with a fairly good formation constant in all of these problems, right? That's sort of the point of using it.
How, at the very end, says find alpha Z2 plus if 3 unfractionated NH3
You do the same thing, except for instead of 0.1, you'd been 0.02 here. Yeah. Yeah. And keep in mind if this value here is within a factor of 1,000 of this value here, your ligand concentration, you may have to make this a more complex form, but that would be very difficult to do, okay? And it's not something you should ever see. If you're seeing that, you really picked the wrong ligand.
So wait, test yourself at the end, it's just like, you're just doing the same thing.
Yeah, that's always the same thing. Yeah, literally, it's because students do these, and oftentimes they just go and look at the solution, but that doesn't tell you whether you understand it, does it?
Yeah, I thought that was like just an extra step ahead.
Nope.
I was just like, oh, what do you do with that?
The test yourselves are always just numbers and answers that you would do the exact same thing as in the solution, and you'd get that answer. It's so that you can see if you missed anything. Literally test yourself. So consider the titration of the zinc 2 plus by EDTA in the presence of ammonia. Again, we would do our titration here. Remember that this is going to give us an activity for the zinc 2 plus. So when you have this secondary ligand, you're going to have an activity for the zinc 2 plus, or your metal ion. This will give us a K double prime, by the way, because we've modified it 2 steps. Okay? Anybody have any questions? All right. I guess we'll start up here next time. I am running a little bit behind on this, which is not great.